Okay. Let me just take the attendance now. We'll start writing. Mahmood. Gafar. Amjad. Sarah.
Here.
Mo. Oh yeah, Mo is, I don't know, something. Daniel. No. Sebi. Sabrina. Elfrida. Arya. Chidi. Yungpeng. Amna. Mariam.
Here.
Okay. Michelle? Michelle? No. Yes, okay. Abir? Yeah. Autumn? Celine? Sophia? Mubarak? No. Shadira? No? Okay. Mohammed? Sabrina? Moza? Angela? Ahmad? No, Safra was here. Neil? 1, 2, 3, 4, 5, 6, 7. Autumn, Mubarak, Shadira, Mohammed, Sabrina, Safra, Neil, and then the other group, Mo and Daniel. Fine. Okay, so to get warmed up, what I want you to use your table book for, you'll need your table book. We have a normal distribution, the usual story, 0 gear and standard deviation 1. So it's the one that's in your formula book. Okay. I want you to find some number in your formula book. We'll call it Z. So that this area here to here is 95%. So I want you to find some number so that the area between these two values is 95%. Now if you were to guess what that number might be, what should it be close to? And remember what I said about how big these graphs are. Yeah, it should be near 2. So see if you can find it. You'll need your formula book. What you get? 1.65 is wrong. And I know what you did wrong. Just to be clear, I think what you possibly gave me is this number here, 1.65, whose area all the way to the left is 95%. It's not quite what I wanted. Me? I can come down to you. Yeah, okay. Oh, well, they're figuring this one out for me, so. Yeah. You got an answer? What you get?
1.96.
That's it, good. So if you work this out, that's 1.96 for this, and let me show you how to get that. So you're looking for the area between z and minus z, and that should equal 0.95, right? But you can't look up you can't look up minus z, so that will be z's value minus 1 minus z's value equals 0.95. Yeah? That's z values minus 1 plus z's values equals 0.95. That's 2 of these, and bring the 1 to the right equals 1.95. Yeah? So that's z's value, what's that? 0.975. So if you go up to the table book and look in the table book, you'll discover that the value when z is 1.96 is the one that will give you 0.975. So these two numbers here are plus and minus 1.96. Okay. If you didn't get that, you should write this down, because this value is actually important. Yeah.
Can I get a copy of the table?
I'm all out. I'll have to print one. They're on Moodle though. Yeah. Okay. Are you writing this down? Do you need to write this down? Yeah. Okay. Continue. Continue, guys. You got it, yeah? Yeah. Yeah. Okay. The reason that this value, have you got that over there, Angela? Yeah. Okay. I can scroll down. Yeah. The reason this value is important, because sometimes you have this type of question. You know, you might have, say, something like height, and the average height might be 160 centimetres, and the standard deviation is 5 centimetres, and you want to know what is the values so that 95% of people are between those two heights. So you want to put 95% of people in a range. So if we call that mu, then the rule is 95% of people will be between the average plus or minus 1.96, and we saw where we got the 1.96 from, times the standard deviation. So you can see why I was saying last week that really 2 and minus 2 kind of represent all of the data. Okay, so let's just take this one as an example. That would be 160 plus or minus 1.96 times 5 centimetres. So what's that? That's 9.8, is it? Yeah? 9.8? 9.8.
Yeah.
So that's, yeah, 169.8. And then at the lower end, it'd be 150.2. Yeah? So what you're saying is 95% of people will be between these two heights. That's what you're saying. So this is a useful common calculation. I showed you how to use the table book to calculate the 1.96. But in the exam, they're happy if students remember that it's 1.96. And you don't have to recalculate it like how you did here to get the 95%. Okay? So you can remember it's just for 95%, it's 1.96 standard deviations. Okay, so this would be an exam question, a simple sort of section A question.
Is there another value that has the number, or just
Well, 95% is the most common. Then sometimes you get 90% and sometimes you get 99%. But that's quite rare actually. I'd say you've pretty much guaranteed that they'll ask you 95%. Pretty much guaranteed. So it's worth memorizing 1.96. Okay, can you write this example down? Okay, can I scroll down? Do you need to see something? Guys, is there something you can't see? Or is okay? Are you sure? Not okay? Is okay? Okay. Just, whatever you do, calm down and don't be overexcited, okay? Right. Can I scroll down? Okay, so the next thing we want to talk about is sample. So, we know in real life, when we have a population, we can't look at everyone in the population because there's just too many people. You know, if I said to you, what's the average height of students in Ireland, or people in Ireland, you know, it would be too difficult to calculate that population average. So what we can do is we can take a sample of people. So maybe we might take a sample of 1,000 people, and we can calculate the average and the standard deviation from this sample. So let's see, the formula for the average, which we would write like this, x with a bar on top, is the usual formula. The sum of all the data divided by, in this case, it'd be 1,000. That's hardly surprising. Now, that's the same true for the population. So let's say n is 1,000, but let's say the population, whatever, we'll say it's whatever population we're looking at, we'll say it's 10 million. So what's the formula for average here? We use this symbol mu, and it's the same. Sum of all the data points over big N. And what you really would hope is that these two should be about the same. But of course, in real life, they won't be. What do you think would make this closer to this? Oh yeah, but what could you do to make it closer? Like, how could you improve this here? Well, larger n here. So, as this n becomes large like this n, your difference between what you get from the sample and what you get from the true situation should be quite close. The difference should be quite small here.
But isn't there a specific formula to find like population types? Not this.
What are you asking me?
There's another formula to find population types.
Yeah, but what are you asking me? What's your question? Okay. Right. I think it'd be good if you can write this down, because there's another half to this. Okay, you got that? So the next formula is you have the standard deviation squared equals, what did we say? It was this one squared added up, isn't it, over n, minus the average squared like that. Yeah? Another way to write the formula, you might remember. Now, it's not as easy to use, but another way to write the formula is like this. The sum of the difference between the data and the average squared all over n. But I think most of the time it's more convenient to use this form. Now, the symbol we use for standard deviation in the sample is a small s. And what's quite different about this compared with the average is the formula is a little bit different. Data minus average squared over n minus 1. So this is a little bit unusual that when you have a sample, you think the formula should be the same as what it is in the population, but it's different in the denominator. It's n minus 1. Now, in the exam, they actually say it's okay. You don't have to use this formula. You can use this formula, the one we just have, with the n. Okay, but I'm telling you that technically, if you were to study this further, like maybe at university in first year statistics, you might be surprised to see it is n minus 1. So I'm telling you now, it really is supposed to be n minus 1, but in the formula book and the exam, they say the students can use this version here, where it's just the regular one with n in the denominator. Okay?
Does it make any difference?
Does make a small difference, yep. So you can use this one in the exam. But I'm just telling you now that technically it's supposed to be n minus 1. So, again, the bigger the n, the better they are. Can I scroll down? Yeah? Okay. So, what we saw earlier, 95% confidence interval is what we're going to do next. And what we saw earlier is similar to this. So I'll give you the idea. It's usually when you have something like you're doing an experiment and you're measuring some data. And each value in the data is supposed to be the same. So some data x where xi is supposed to be constant. I give you an example, e.g. measure height 10 times. If you measure the same height 10 times, you should get the same number 10 times. An example from physics is if you swing a pendulum of length 1 meter and measure the time 10 times. You should get the same time each run of the experiment. And I don't know if you did this in any of your chemistry or biology experiments. When you performed a measurement, was it always of something different, or did you ever measure the same thing 2 or 3 times? Did you? So yeah, like can you think of anything that you measured that was supposed to be the same and you measured it more than once and recorded it? Temperature?
Yeah.
So you'd make some measurements of temperature. How many times?
3.
Measure temperature 3 times. And did you get the same number each time?
No.
No, but this is close.
Yeah.
Yeah? So this is where the idea of a confidence interval comes from. It's where you have data and you want to try and estimate what the true answer is. And you can't know for certain because each time you measure, it's a little bit different. Okay? So, for example, here's our data. You measured temperature 3 times, was it? So maybe it's 50.1, 50, and maybe 50.2 as an example Celsius. Can I scroll down a little bit? Okay, so you probably know this from doing the experiment. What is the best value you should use from these 3 as your answer for the temperature? Which one? Why? It's the average, yeah. So your best estimate is the average. 50.1 plus 50 plus 50.2 all over 3, which is 50.1 Celsius. That's usual. Now, this is the new piece for this morning. What I want you to do next is to calculate the standard deviation of these 3 numbers. I'll just give you a minute to do that. So standard deviation. And you're already halfway finished because you know the average. You got a calculator. What you got?
98.
Wrong. Okay, so you'd stop right there. This should be a decimal. It should be quite small, you know, like 0.1 or something. What'd you get?
0.82.
Okay, so it was 50.1 squared plus 50 squared plus 50.2 squared over 3 minus 50.1 squared, and you got 0.082 if we round it off then. Yep. Now here's the new thing to calculate, something called the standard error, SE, standard error. And the formula for that is the standard deviation divided by square root your sample size. So for this one here it would be 0.082 all over root 3. So that would be smaller again. 0.047 Celsius. Now let me explain what that number means. So let's imagine our bell curve, and sitting in the middle of the bell curve is the our average, what was it? 50.1. Okay. Now each time, well, maybe I won't write 50.1, I'll just write the true average there actually. So you understand that when you do the experiment, and then when she does the experiment, and when he does the experiment, you all get a slightly different average. So maybe he gets 50.1, maybe I do it and I get 50.11, maybe someone else does it and they get 50.09. So the average is actually changing a little bit. In fact, the average has a standard deviation, which is this, what we call standard error. So in other words, each time I do the experiment and get an average, it should change a little bit. It changes actually by this much. You can use the formula I gave you at the very start. 50.1 plus or minus 1.96 times 0.047. Or in other words, your average from your data plus or minus 1.96 standard deviation over square root n. This is a way to put boundaries on what you think the true average is. Because like I said, you understand that each student will have a slightly different average. You don't know what the true average is, but at least you can say 95% of the time it's between these two numbers. So 95% confidence interval prediction. What is this, please? It's two values. $52 seems a bit big.
So for the negative,
What's the negative one?
negative 150.007.
Say again?
50.00.
50.008. So basically 50. Yeah. Yeah? Yeah, exactly. This is the error bars. Did your graph in chemistry, when you had to graph, did you have to graph this in the chemistry?
I didn't, but I did this last year.
Oh, last year, okay.
Ecology and
Yeah. This is like the error bars. And in fact, it is the error bars.
I know, I distinguished the SE.
Yeah. Did Lorraine ask you to calculate error?
Yeah.
Now you see there are other formulas like this to calculate it. This is the most precise, but the other formulas which Lorraine probably had you use is pretty close to this. Like what was the formula she had you use?
She didn't give a phone.
Are you sure? Like if you had three numbers, how would you calculate the error?
She did the calculation once.
Do you remember the formula? Like maximum minus minimum, anything like that? No? More or less complicated than this? More?
We have to do more stuff.
Okay. Are these... Yeah, so where did you get the plus or minus 0.05? From the instrument. Ah. Yeah, that is harder. Yeah, but I suppose the difference is in this version here, you actually have an error with the equipment that you know of. Whereas in my example here, I'm imagining those values were measured exactly, and the error is caused by some other thing other than the measuring device. So you have two errors to consider: the fact that it's varying and that the machine can't measure precisely. So that's why it's a longer calculation. Okay, so just to finish this one here, what you would say as like a 1 mark, you know, in the exam, just wait 1 second and then you can. What you would say for like 1 mark in the exam is what is the meaning of this result, and the answer would be, you would say that the 95% of the time, the true temperature is between, what's that, 50.01 Celsius and 50.19 Celsius. These represent limits on your prediction of the true temperature. I rounded it off. 50.01, yeah. Okay? So there's only two new formulas for this lesson. This one And this one, for confidence interval, it's the average plus or minus 1.96 standard errors. And this is the formula for standard error which you can use. So if you want to just write it as one formula, it would be average plus or minus 1.96 sigma over root n. Yeah?
That one is to find
Which one?
the second formula.
This one?
To find what the true number is 95% of the time.
Yeah, it's to put, you know, when you make a prediction, you want to say plus or minus some possible error. So yeah, you're trying to put a limit on your prediction. It's kind of like when you see in surveys, you know, they might say 20% of people voted yes, and then in the small print it would say plus or minus 2%. It's like this. Yeah, it's a constant representing 95% confidence interval. Now, it's very, very unlikely that they will ask you a different, because 95% is the standard amount. But just in case, it's very unlikely, but in case they ask you for 99%, you would have to go through this process that you did at the start again, but replace that number with 0.99 to get a different answer here. Yeah? Yep. No, you can only ask me one actually. So pick between the two, which one? Okay, you can save it for later. Yeah. Oh, you need to go, yeah. Okay, yeah, there's a few minutes left. This is good. So the next lesson is quite difficult. This one is more just a calculation lesson. You can try some of these. My advice, you should definitely do the questions that mention 95%, but it's enough if you just want to do one of the questions that mention a different percent than 95, just so you can practice in case it happens in the exam. But I think most of these I make 95. Do I?
90%.
Which one? There's a 90 and there's a 99, and a 95 and a half.
So, sir, for
Yeah.
99, it's 0.995 values.
For what? For 99
Take the value of Z
is what?
and get you 0.995 for Z. So, for this one,
No, I'll pause you. I'll hit the pause button there. You need to go through this process at the start again. Did you?
yeah,
Are you sure? Because it sounds like you did something wrong.
that's
Good. Good call. Can I close this? Yep. Yes. Well, let me just save this first so I don't forget.